Oh, wow. Another week, another quiz. Okay, time for quiz 11. You could say that this is the penultimate quiz because, well, it's the second to last, right? All right, so 10 problems. Let's see how we do. Number 1, determine if the sum from 1 to infinity cosine pi halves n over root n diverges, converges conditionally, or converges absolutely. Well, let's think about what we have here. It's a little strange. Now, whenever you see something like this cosine pi over 2n, you want to be a little bit careful because, well, how is that behaving? Now, we should point out that cosine of n, that behaves erratic and moving back and forth. Okay, well, that's not what we have. And the problem is with cosine n, you run into troubles. Now, cosine of pi n, that actually has really nice behavior. For example, if n equals -1, you get cosine of pi, which is -1. n equals 2, you get cosine 2 pi, which is 1. It turns out that that's -1 to the n. But that's also not what we have. So, before we start to answer this question, let's try to understand better what sum we actually have. Because it's good to understand what you have. So, cosine pi over 2n divided by root n. Okay, now, what's the important thing? Well, do the first couple terms, see if we can spot a pattern. So, cosine pi halves. Cosine pi halves is 0 over root 1. n equals 2. Cosine of pi, well, that's -1, so -1 over root 2. All right, 3. Cosine 3 pi halves is 0. So we're going to get 0 over root 3. Okay, how about n equals 4? Cosine 2 pi, well, that's +1 over root 4. Cosine 5 pi halves will be a 0 again. So 0 over root 5. Cosine, let's see what we're up to, 6 pi halves. Well, that's the same as cosine of 3 pi, which is really the same as cosine of pi. So that's a -1 over root 6. 7 pi halves, back to 0 again. And so forth and so on. Now, what's happening here? Well, what's happening is when we do this sort of multiples of pi halves, we're going between sort of 4 different locations. And so we start at 0, -1, back to 0, back to +1. Because we're doing the cosine, so the cosine deals with the x values. So again, 0, -1, 0, +1, 0, -1, 0, +1, so forth and so on. Now, question, does this alternate? Well, not really. See, the problem is the zeros. So, idea. Let's get rid of the zeros. Certainly, if we get rid of the zeros, then that'll help us understand what's happening. And throwing out the zeros is okay. We're still adding up the things in the right order. And no matter how many times you add 0 and you get 0. So really we can say, look, this is -1 over root 2, +1 over root 4, -1 over root 6. The next one would be +1 over root 8. And now, yes, now we are alternating. Okay, good. So, alternating sum, what would we have? Well, we'll go from 1 to infinity. The top, we start off negative, positive, negative, positive, negative, positive. That's -1 to the n. The bottom is what? Well, square root of 2, square root of 4, square root of 6, square root of 8. Those are the square roots of the even numbers, 2, 4, 6, 8. Who do we appreciate? Math. Math. Oh, sorry. Got distracted there. So, even numbers are 2n. All right. Now, so this sum equals that sum. Good. So the question is, does this sum converge? And the answer is Yes. Well, why does it converge? Well, this sum converges because this is an alternating sum, and the terms go to 0. And so, by alternating series test, this converges. Now, are we done? No, we're not done yet. The problem is, we know it converges, but we don't know how it converges. See, because there's really two flavors of converging now. There's conditional convergence, see conditional, and there's absolute convergence. So, to determine which, we say, okay, now look at the sum if you didn't alternate. So 1 to infinity of 1 over root 2n. Now, to simplify, the 2 there is a constant, you can pull it out. So 1 over root 2, sum from 1 to infinity of 1 over root n. Now, what happens to this? Do we know? Yeah, we do. Why? Well, it's a p-series. And this diverges. And the reason it diverges, if you look at the exponent, it's n to the 1/2. So, the original sum converges by alternating sum test. The absolute value of the sum diverges by p-series. So if we put that together, we come to the conclusion that this is conditional convergence. And that's our answer. Good. Good. Woohoo! One down. Progress. Progress. All right. Let's do the next one. Number 2. Determine if the sum -1 to the n over n log n diverges, converges conditionally, or converges absolutely. Very similar problem. Now here we already see it's an alternating sum, and we say, look, it alternates, n over log n downstairs, it's getting bigger and bigger, which means the whole thing goes to 0. So we can say, by alternating series test, this will converge. Okay, so that's good. So we're halfway there. In other words, we can toss out the divergence. Now, are we done? No. No. Now we got to say, well, what happens if we took out the alternating part? All right. So what can we say about the sum n equals 3 to the infinity of 1 over n log n? Now, the thing is, 1 over n is right on the border. And so because of that, you got to be a little bit careful. Because it's right on the border, just a little bit more might be enough to knock it over to converging. And we do have a little bit more. But is it just enough? Well, how do we figure it out? The answer is, we're going to use an integral test. Now you might say, how do you know to use the integral test? Well, I'll tell you, the secret is that the integral test is custom built for sums like this now. 1 over n and then some log n's floating around. That's one reason I know. But the other thing is, every other test is really going to be sort of inconclusive. If you do the root test, you'll see the limit is 1, inconclusive. The comparison test, we'd like to compare it to 1 over n, but the problem is it compares in the wrong way. And unfortunately, that log n, it's just, there's not a good comparison to make. So let's try the integral test. Well, that would be 3 to infinity, 1 over x log x. Now, hopefully you can sort of start to spot. It's like, oh yeah, if this was what I had to integrate, I could make progress here. Maybe I wouldn't jump right to the answer, but I could see some things. For example, if we were to let this log of x be our u, then the 1 over x dx would be our du, meaning that we're setting ourselves up for a really good substitution. And in particular, this would be the integral of 1 over u du. Our bounds would have to update, so log of 3 infinity, well, what happens to log as you go to infinity? It goes to infinity. So this becomes log of u from log of 3 to infinity. Now, we don't care what happens at this end. It's the infinity end that matters. So what happens to log as we head off to infinity? The answer is, it gets huge. So in other words, we can say that our conclusion is the integral diverges. And the nice thing about the integral test is it really is a two-way street. See, I really should say I can go back and forth. Not in so much what the answer is, but in terms of the behavior of the answers. So that says that the sum diverges. So this is a case where the series itself converges, alternating series test. Take away the alternating part, it now diverges by integral test. And if we put that together, our conclusion is it is conditional convergence. All right. Wow. 2 conditional convergences in a row. Okay, well, we could have 3 or 4. You know, don't try to guess patterns. Look at what the problem says. The problem will tell you where to go. All right, number 3. Determine if the sum from 1 to infinity of minus 1 to the n over root n plus n squared diverges, converges conditionally, or converges absolutely. Well, alternating, negative 1 to the n, terms here, you're going to get really huge denominator going to 0. So we know that this converges, and that we can see that by the alternating series test. Okay, all right, no surprise so far. We've seen this story before. Now, let's get rid of it. And when I say it, I mean the alternating part. So that's the sum, 1 to infinity, of 1 over root n plus n squared. Now, the question is, does this converge or diverge? So, remember when you have a plus sign, what you really say is, look, let's ignore the smaller stuff. So between the root n and the n squared, what's the smaller stuff? Well, it's the root n that's smaller. So if we were to sort of cover that up, we'd say, oh, it really looks like 1 over n squared when n is large. And that's converging. So we think this converges. So now we just have to prove it. And now I say, well, we could do a limit comparison, or maybe just a comparison. Because notice, these terms are being added together. So if I just delete the small stuff, I'll end up with something which is bigger. And of course, the term itself is greater than or equal to 0. Now, this part, we have that the sum from 1 to infinity of 1 over n squared converges, and the reasoning is p-series. So we want to make sure we understand why things are true. We don't want to just say, well, it looks like it's good to me. We want to justify. And therefore, by comparison test, since we know something bigger than it converges, then the smaller thing converges. And so now we get that, aha, we didn't even need the alternating to converge. It would have done it anyways. So that says, look, the conditional here, that word conditional, means it really depends on having that sign change. Since we don't need that sign change, our conclusion is that we converge in the absolute way. So absolutely converge. And that's our answer. All right, cool. All right, next one. Number 4. Find the radius of convergence for the sum 0 to infinity n factorial squared x to the n over 2n factorial. All right, so notice our center here. Our center, it doesn't ask us for it, but we can just say it really quick. That's at x equals 0. So what we're looking for is we're saying it should converge for absolute value of x less than r. This is the radius that we're after. That's what we're trying to find. Because we see the factorials here, we know at the start we're going to be using the ratio test. So factorials tells us use the ratio test. And so here's our basic idea. We're going to think of this whole piece as our a sub n. And we're going to take a limit as n heads off towards infinity. Absolute value of the next term divided by the absolute value of the current term. So that's the limit, n heading off to infinity of what? Well, be generous with your parentheses here. We're going to, everywhere we see an n, we're going to replace it by n plus 1. So n plus 1 factorial squared absolute value of x to the n plus 1, because the only place where absolute value comes into play is the x. Divide that by 2 times n plus 1 factorial. Then multiply by the reciprocal of a sub n, so 2n factorial n factorial squared absolute value of x to the n. Now right away you see that some things simplify very nicely. I can cancel almost all the absolute value of x's. I would just be left with one of them. And since that doesn't depend on n, I can even pull it out. So I have an absolute value of x on the outside now. Now what do I have left? Well, the n plus 1 factorials, I'm going to try to cancel out with the n factorials. So I'm going to rewrite that as n plus 1 times n factorial. So that's my n plus 1 factorial squared, and I'm going to divide it by n factorial squared. We'll clean that up in a second. Now the 2n factorial upstairs, well, what I can do is I can come to this downstairs term and notice that this is really, downstairs, it's really 2n plus 2. So when I think of doing the factorial with that, that's going to make that 2n plus 2, 2n plus 1. I just keep pulling off terms until I get to 2n, and then I say that's a factorial. Now we get some cancellation. 2n factorials cancel, the n factorials cancel. Ah, life is good. In fact, we can go a little bit further. See this term here? That's really 2 times n plus 1. And now there's an n plus 1 squared, and there's an n plus 1 downstairs, so you can cancel one of those with one of those. So, what's left? Well, what's left is you have absolute value of x, limit, as n goes to infinity. And even if you hadn't canceled everything, you'd still be able to get to something relatively simple to work with. There's a single n plus 1 left upstairs. Downstairs there's 2 times 2n plus 1. All right, then it's 4n plus 2. And this is a case where you can look at the leading coefficients. When it's polynomial over polynomial, you say, well, what are the leading coefficients? And of course, that's if they're the same degree. And here, they're both degree 1. So absolute value of x times a fourth. Now remember, this, because of we're doing the ratio test, this limit converges as long as the result is less than 1. Or I can say the absolute value of x is less than 4. Now I'm in the right format. And therefore, there's my radius. So the radius of convergence is 4. Now what happens at the end? Ooh, that's tough. That's tough. But the good news is we don't have to find the interval. So it's okay if we don't know what happens at the end. All right. Next one, number 5. Find the radius of convergence. Okay, so x to the n, 1 plus 1 over n to the power n squared. Okay, what happens to that? Well, you might think, what's the right test? Well, the nice thing is, when you're looking for radius or for interval, well, okay, what can you do? But when you're doing the radius, there's only 2 tests. The root test, the ratio test. The ratio test, if you see a factorial, you have to do it. Otherwise, you have some freedom, but generally speaking, if you see everything involved having exponents involving n, in this case, they both have exponents involving n. All right, so stuff to the n, that tells us we should use the root test. All right, so that's what we're going to do. So we're going to take a look at the limit as n goes to infinity. We're going to think of this whole thing here as our a sub n. So absolute value of an to the 1 over n. So let's just carefully unwrap this. So we have absolute value of x to the n times 1 plus 1 over n to the n squared. I don't need absolute value on this part because that part's never negative. And so I'm going to take all of that to the power 1 over n. So what happens? Well, do them separately. Absolute value of x to the n to the power 1 over n. You multiply the exponents together, n times 1 over n becomes 1, which means that you'll just have a single absolute value of x. Go ahead and pull it outside the sum. Sorry, pull it outside the limit. What about the other term? Well, it's still going to have n, so it's 1 plus 1 over n, but to what power? See, n squared to the 1 over n means you're going to multiply. So it'll be n times 1 over n to the n power. Now what happens to this? Well, this should be a limit we know. Do you remember it? It would make you quite happy to know this limit. Yes? I think it would make you very happy to get the answer, right? Yeah, it's E. Yeah, good, good, good. Why? Well, this is something we did where we used L'Hopital, and in general, you should recognize that 1 plus something over n to the nth power is e to the something. And again, this is a very straightforward exercise with L'Hopital. As with the last problem, when we do the root test, this will converge when we're less than 1, or that says when absolute value of x is less than 1 over e. And so here, that's our radius of convergence, 1 over e. All right, that's good. Hey, these are kind of good. Wow, man, I kind of miss not having quizzes. The good old days of quizzes. I remember those. It felt like just a few weeks ago. Okay, number 6. Find the radius of convergence for nx squared to the n over n factorial, where we go from 1 to infinity. Now you might say, ooh, I see an nth power. That should be a root test. Wait a second, I see a factorial. That should be a ratio test. Well, what's the right test? The answer is, it's going to be a ratio test. Factorial is just, once you see it, there's no more debate. We're like, okay, factorial it is, my friends. All right, well, let's do it. Let's see what we're going to get. All right, so we're going to do a ratio test. Here, this will be our a sub n. So we're going to take the limit. N goes off to infinity. Absolute value an plus 1 over absolute value an. So that's our limit as n heads to infinity of what? Well, everywhere where I see an n, I'm going to put an n plus 1. So, and then don't forget the absolute value. So let's see, we're going to have n plus 1 x squared. I'll put an absolute value there. I don't really need it because it's being squared, but I'll still do it. It's good practice. To the power n plus 1. Divide that by n plus 1 factorial. Then multiply it by the reciprocal of an. So that's n factorial. And then n absolute value of x squared to the nth power. All right, now, let's see what we can get here. Well, this is limit n goes to infinity. I'm going to go ahead and just take the powers here. So this is n plus 1 to the n plus 1. And downstairs, the corresponding piece would be n to the n. Well, those aren't quite the same. Okay. I still have the absolute value of x. Upstairs, I'd multiply, so that would be 2n plus 2. Downstairs, it'd be just 2n. Okay. The factorials Well, upstairs I have n factorial. Downstairs it's n plus 1 factorial. But in anticipation of wanting to cancel, we'll pull off a single n plus 1. And now we say, boy, it would be nice if stuff cancels. Well, on the first term, nothing cancels. Ah, so close. Okay, all right. How about the second term? Good news is we do get cancellation. So we're left with just two absolute values of x's. On the last term, the factorials cancel. So we're left with a single n plus 1. And now I say, hey, wait a second. There's a little bit extra cancellation, right? Because I see an n plus 1 up there. In fact, I see a bunch of n plus 1s there and a single n plus 1 down here. So if I cancel this n plus 1, I'll get rid of one of those up there. Now it's our great moment. So the absolute value of x squared can come out of our limit, just like what we've been doing with other problems. So absolute value of x squared, limit, n goes to infinity. Now the only thing that's left is this piece right here, but both terms are raised to the nth power. So I have something to the n, namely n plus 1 over n. But that can be rewritten as 1 plus 1 over n. So this part right here, this inside part, this is really secretly just a simplification of n plus 1 over n. Now, at this stage, we're like, hey, we just did this like one problem ago. And our memory is at least good enough to last for one problem, sometimes even two. So that is going to go to E. And when we're doing the ratio test, this will converge when we are less than 1. So that says we need absolute value of x squared to be less than 1 over E. Now, is this our answer? And why not? It's not our answer. Good. Why not? See, the problem is that square. You got to somehow account for that square. So we don't want a square there. So how do we get rid of a square? Well, the way to get rid of a square is to use square root. So take the square root of both sides. We get absolute value of x is less than the square root of 1 over e, which we can just write as 1 over the square root of e. And that is our radius. That's what we're after, is the radius of convergence. Nice. Cool. We are making some progress. Woohoo! Wow, we're already like 6 problems in. That's amazing. Wow. All right. Well, let's keep it going. Let's keep it going. Number 7. Find the interval of convergence for the sum n equals 1 to infinity 2 times x minus 1 to the nth power over n squared. All right, root our ratio test. Which one should we use and why? Well, we can use both, but in this case, I think that this is probably a good argument for our root test. I think root tests tend to work out fairly more straightforward than most other tests. Now, it's probably good to recall, and I'm going to go ahead and write it now. What happens to n to the power 1 over n? Do you remember? N gets big. This is going to go to 1. That's not so clear, right? Because really, if you were to think about it, what's happening is you have a really huge number to a really small number. So it's like infinity to the 0. And infinity to the 0 is a classic example of more work. Well, but we do the work once and then we remember it. Okay, so here is our a sub n. So we're going to apply the root test, and we have the limit as n goes to infinity of absolute value of an to the 1 over n. Well, that's the limit as n goes to infinity of, well, take the absolute value here. That'll be 2 absolute value of x minus 1 to the nth power divided by n squared. We're going to take all of that to the 1 over nth power. Now, if we take that, well, the numerator, really nice, like really, really nice. Like the kind of nice you want to take home and meet your family. Downstairs, not so nice. Not the worst. So I have a power to a power. N to the power 2 to the power 1 over n. Now the thing is, there's a couple things you can do. You can either combine the powers together, or you can say, look, I'm going to choose which order I take my powers in. And here, we can say, well, look, this is like n to the 1 over n squared. So this n to this 2 to the 1 over n is the same as n to the 1 over n to the 2. And the reason we want to do that is we want to use our nice little fact. So we say, hey, the top, well, it's always going to be 2 absolute value of x minus 1. And the bottom, this little piece down here, goes to 1. So that's the limit. And that will converge when this is less than 1. That's what the root test says. So let's clean that up. We get absolute value of x minus 1 less than a half. And then we can say, all right, well, that says minus a half is less than x minus 1 is less than positive a half. Now add 1 to the 3 different sides, and we'll get that negative half plus 1, which is 1 half, is less than x is less than 3 halves. Now we're not done yet. What we know for sure is in between these 2 points, 1 half and 3 halves, we're going to converge. And we're going to converge in a really nice way. If I'm bigger than 3 halves or I'm below a half, we already know it's going to diverge. But the question is, what happens exactly at those points? So, how do we figure that out? Well, we've got to test the endpoints. And we have to test both of them. So, let's plug in 1 half. So, let's just go ahead and do the computation here. A half minus 1, that's negative a half. And then if we double that, that's negative 1. So this becomes the sum from 1 to infinity of negative 1 to the n over n squared. Now, on a side note here, notice that this sum really doesn't involve anything very geometric. The negative 1 to the n, it's not really geometric, it's just sort of saying alternates your sign. And this will often happen at the endpoints. Anything that looks geometric will very likely disappear. And if it doesn't seem like it's disappearing, you should be really careful and double check your work. Now, does this converge or diverge? Well, it's an alternating series, and the terms go to 0. So, alternating series test says converges. And so we're good. Now, we can use other tests, but remember, we're not asking conditional convergence, absolute convergence, we're just saying convergence. So we don't need to do it anymore. How about at 3 halves? Well, 3 halves minus 1 is a half times 2 is 1. So what we end up with is the sum 1 to infinity of 1 over n squared. Well, that's a p-series. Now, is this p-series converge or diverge? Well, it converges because the exponent is bigger than 1. Now, that says we converge at both endpoints, so we're going to include both endpoints. So our final answer is 1 half less than or equal to x, less than or equal to 3 halves, because we want to toss in our other endpoints. And that is our interval of convergence. You could, if you wanted to, if you like the notation 1 half comma 3 halves, you can also use that notation as well. That's perfectly fine. No worries. All right, good. Number 8. Determine the x for which the sum 1 to infinity x squared minus 5 to the n, divide that by n, 4 to the n, converges. Okay, it's a curious looking sum, and well, we'll work on it. We'll see where we end up. Now, if we look at this sum here, well, we see lots of things raised to exponents, no factorials, So that's sort of the idea of saying, let's use our root test. So we're going to do a root test. And what do we get? Well, we're going to take the limit as n goes to infinity, absolute value of an to the 1 over n. So this is our limit as n goes to infinity of, in the inside, it'll be absolute value of x squared minus 5, because that could be negative, to the n over n 4 to the n. And then we're going to take that to the 1 over nth power. All right. Well, what does that tell us? Well, n to the 1 over n. Okay, yeah. So if we clean this up, we get absolute value of x squared minus 5 in the numerator. Nice. N to the 1 over n. Also nice. 4. And we say here, that's the only place where n shows up, but we know what that does. So we're basically done. So that's x squared minus 5, absolute value over 4. And that will be less than 1. All right. So this will converge when the absolute value of x squared minus 5 is less than 4. Now, what does that tell us? Well, it tells us that really we have two interesting points. Let's think about our endpoints for a second. So our endpoints will be when x squared minus 5 equals 4 and x squared minus 5 equals negative 4. So really, the question is, if you have absolute value of x squared less than something, your endpoint is when the absolute value equals something. So suppose we look at the equals 4 first. Okay, if it equals 4, this would become the sum 1 to infinity of 4 to the n divided by n 4 to the n, which is the sum from 1 to infinity of 1 over n. What do we know about that sum? That sum diverges. Why? We should know this one. It's the harmonic sum. Okay, how about the negative 4? Well, if we do the negative 4, what's the difference? Well, the difference is you're going to have minus 4 to the n over n 4 to the n, which is the sum, 1 to infinity, of minus 1 to the n over n. Now, does that sum converge or diverge? And how do we know? Well, it converges. Why? Well, alternating series test. Because that plus minus 1 behavior up in the exponent, and also the terms go to 0. So that says what? Well, it will converge when x squared minus 5 is equal to negative 4 and diverge when x squared minus 5 equals 4. So we get to the point here. Negative 4 less than or equal to x squared minus 5 less than positive 4. Now, if we add 5 to both sides, that will say 1 less than or equal to x squared less than 9. Now, let's think about what that means. So, if we were to do a quick sketch here, the function x squared, we know what that looks like. It looks like a parabola. And the reason it looks like a parabola is because it's a parabola. So that's a good reason why. So we're asking, when does x squared, when is it between 1? So let's say here this is 1, and let's see, 9. So let's say this is at 9. Now, that says, I really want to be in this range, but I should be a little bit more explicit here. So I'm going to switch my colors for just a second and say, this line, solid. We're going to do it as solid. And this line, dotted. So the question is, well, when does x squared land in between these places here? All right. Well, I think we can figure this out. So, when does x squared hit the value 1? Well, it does it at minus 1 and plus 1. When does it hit the value 9? Well, does it at 3 and at minus 3. So, see, if we were just to take the square root of everything, we'd be like, hey, isn't that 1 less than or equal to x less than 3? And that's exactly what this is saying here. But remember, x could be negative, so we want to be making sure we don't miss anything. So the answer is negative 3 up to and including negative 1, and 1 up to and including 3. All right, and that's the answer. That is the correct choice. Those values of x, we definitely converge. Other values of x, we definitely diverge. But there should be something here that's making you stop and say, wait a second. I feel like you've misled us somewhere along the way. What's true about this? Notice this is not an interval. See, an interval says you're going to start at some point, go to some other point. You may include the endpoints or not. But this has two distinct pieces here. And intervals will just have one. So this is not an interval. So this does not converge for some interval. But we've said before that all power series will converge over some interval. So why does this fail? The answer is this right here is actually not a power series. So that's a good reason why it doesn't fit the mold, because it's not actually a power series. And so be a little bit careful here. Now we were okay. It feels like it should be an infinite polynomial, and in some sense it is, but not in the normal way that we usually write a power series. So be careful. Be the right amount of careful. That's why we like to do problems like this on the quiz. It really gets us thinking, gets the blood flowing, which is good. All right, 2 more to go. Number 9. So we're going to say that for absolute value of x less than 1, find the power series for log of 1 plus x squared. Oh my gosh, they even gave us a hint? Whoa, that's unusual for them. Well, okay. So how are we going to do this? Well, the thing is we don't want to reinvent everything from the ground up. So the question is, how can we connect to this function natural log of 1 plus x squared? How can we connect this to something else we already know? So that's oftentimes what we do. Let's connect this to something else we already know. This is the problem of trying to talk and write at the same time. So the goal is, look, if we can connect it to something we already know, it speeds it up because we don't have to start from scratch. And the good news is, for better or worse, we know very little. And so that's great. When you don't know very much, it basically says you have to do certain things. So what do we know? Well, about the only thing we do know is that 1 over 1 minus something is equal to the summation from, let's say n equals 0 to infinity of something to the n. Now I'm not using the symbol x because I don't want us to get tied down to x. The key is that we have this mold, that we can put something inside of here. It could be x, could be some other expression, and whatever fits into there, that's what goes up into that box. So what's inside the box? That's the question. Now, notice they told us how to start making our connections. Start with the derivative. And we probably would have guessed that, because really what do we have? We have algebra, which allows us to sort of combine things, break things apart. And we have trig identities sometimes, but we don't have many trig identities here. We've got arithmetic, and we've got calculus. So calculus looks like a good candidate. And so I'm going to think of this function right now of f of x as log of 1 plus x squared. So f prime of x, derivative of natural log, is 1 over 1 plus x squared times 2x. Now, you'll notice there's a 2x here. For this 2x, just leave it alone. I'm going to think of that as a polynomial. And in fact, that's why we want to leave it alone. Because when we're thinking about a power series, we're really thinking about a polynomial. So this is our polynomial. We're happy with that. The part that's we're not happy with is this other part here. And so we got to think about 1 over 1 plus x squared. What can we do to that part? Well, now we say, can we make it 1 over 1 plus x squared look like 1 over 1 minus something? So I'm going to write the 2x in front and say, well, there's definitely 1 over 1. I don't want a plus, I want a minus. So I say, well, what has to go here? So I match that. Well, minus x squared. Now I say, aha, there's my mold. That's what we're putting inside, minus x squared. So this will give us 2x. Again, that's just the part in front. Sum 0 to infinity of minus x squared to the nth power. And now, here's the part that's fun. This 2x out in front, because it's a polynomial, I can multiply it through. Really, I can just think about distributing. So if we do that, what do we have? This will be the sum, n equals 0 to infinity. There's a 2. And I'm going to break this up. There'll be a negative 1 to the n. Then I have a single x, and now I have an x to the 2n, because I multiply those exponents together. So that's x to the 2n plus 1. All right, so let's gather ourselves here. We now know that f prime of x is equal to the sum from 0 to infinity. We have a 2, negative 1 to the n, x to 2n plus 1. So now I have a nice series for f prime. To finish up, I want to get a series for f, natural log of 1 plus x squared. So to go from f prime to f, we would take an integral. So f of x is sum, n equals 0 to infinity. The 2 times negative 1 to the n is a constant. It doesn't depend on x. X is the variable that we're differentiating or integrating with respect to. N is the index. It's not a variable. We don't differentiate or integrate with respect to n. Well, okay, that's a different story. I was going to say a sum can in some sense be thought of as a kind of integration, and if you can get into that philosophy, it really makes things work really well. But all right, different thought. How do you integrate x to 2n plus 1? Well, you add 1 to the exponent, so x to 2n plus 2, and then you divide by your exponent, 2n plus 2. Now, at the very end of this, there's always going to be a c, because if you do an antiderivative, you get a plus c. To figure out what c should be, so we need to plug in, and we plug in our center, x equals 0. We get f of 0. Well, f of 0, that's log of 1, which is equal to 0. When we plug 0 into this expression, all the terms are going to be 0 because it's 0 to a power, so we get 0 plus c. And so our answer is, well, the c is gone. Now, notice this 2 times n plus 2. I can factor 2 out, n plus 1. And then I could cancel off a 2. So we get that this is the sum from 0 to infinity of minus 1 to the n, x to the 2n plus 2 divided by n plus 1. And that's our answer. Now you might say, hey, there were 2 answers on the answer sheet. Okay, you've been looking at the answer sheet. Cool. How do you get to the second answer? Well, if you stare at this expression, you'll see that there's really a lot of n plus 1s, because there's an n plus 1 up here, downstairs. 2n plus 2 is 2 times n plus 1. So what we can do is we can sort of introduce a change of index. So I'm going to make n plus 1 something new. I'm going to call it k. So let's see what happens. When n is 0, what does k equal? Well, k is n plus 1, so k equals 1. As n goes to infinity, what does k do? Well, it goes to infinity plus 1, but that's really just infinity. Okay, so far so good. The n plus 1 downstairs, well, that's k. X to the 2 times n, 2n plus 2, that's 2 times parenthesis n plus 1. So that's x to the 2k. Now, how about this negative 1 to the n? Well, what I can do here, I can say that k minus 1 equals n. So I can write this as minus 1 to the k minus 1. And that's the same expression. It really is the exact same. The only thing that's happened is we've just shifted our index. So instead of starting at 0, we start at 1. But if you were to write out the individual terms, everything matches up. So which one is correct? The answer is that these are both correct. Which one do you need to write down? Well, whichever one you like to write down. So that's what you can do. You can write down one, the other, or both. So yes, it is possible to express your answer in more than one way. Isn't that beautiful? I like to think it is. Number 10, our last one. Wow, whew, time's really flown in this quiz. Express the sum n equals 0 to infinity n squared x to the n as a rational function. In other words, a polynomial over a polynomial. And find the sum n equals 0 to infinity of n squared over 2 to the n. Ooh, it's a 2-4. We get to do two different things. Nice. This is the problem so nice, we get to do things twice. Okay, so let's begin. Let's start with thinking about how do we get to this n squared x to the n as a rational function. Well, start with what you know. What do you know? Not much. In fact, pretty much the only thing we do know is that if we have 0 to infinity of just x to the n, that's equal to 1 over 1 minus x. Okay, we know that. Well, that's good. We start there. And now we say to ourselves, okay, well, what's the difference? Well, the difference is the n squared. So you're like, aha, multiply both sides by n squared. No. That can't work. See, the problem is n squared is not one single thing. N varies here. Sometimes it's 0, sometimes it's 137, sometimes it's 1,000,000. So I can't multiply by n squared there. I definitely can't do it there because it's kind of a meaningless thing. So it's like, darn it. All right, what else can we do? Well, arithmetic and algebra don't seem to really help much. Let's think about calculus. Is there something I can do to x to the n so that I can make it look closer to n squared x to the n? Well, a nice calculus tool is the derivative, right? Because if we take the derivative, the exponent comes down, that would put an n in front. So, idea, take the derivative. Now, whatever we do to one side, we do to the other side. And as long as we're consistent, we'll still have equality wherever the convergence happens. So n, x to the n minus 1. So, how do I take the derivative of that right-hand side? I'm going to think this as 1 minus x to the minus 1. So the derivative would be, let's see, minus 1, 1 minus x to the minus 2. See, comes down, subtract 1. Multiply by the root of the inside, which is minus 1. That would be minus minus makes a plus. 1 over 1 minus x squared. All right. We say, well, what could we do here? Well, we could take another derivative. We could do that. Oh, that would be an interesting exercise. But before we do that, we say, well, I really don't want x to the n minus 1. I really want x to the n. So let's make it x to the n. Well, how do I make it x to the n? Well, I can, you might be saying, hey, integrate both sides. No, 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 no. We don't want to take a derivative and then take an integral. That gets us into a circle. We don't want to get into a circle. Really, we're just short one x. And we're always short consistently a single x. So we're going to multiply both sides by x. So I'm going to write this dot x is times by x. And now we get the sum, 0 to infinity, n x to the n equals x over 1 minus x squared. Aha! Success! So by taking a derivative and multiplying by x, we have brought down a single n. But I wanted to bring down two n's, because I need to get to n squared. Well, let's do it again. So, take a derivative. That'll give us the sum from 0 to infinity, n squared times x to the n minus 1. Right? Why n squared? Because the n comes down, n times n is n squared. All right, on this other side, probably we should use a quotient rule. So let's see. That says take the bottom times the root of the top minus the top times the root of the bottom. So that's 2. 1 minus x to the 1 times minus 1. All of that divided by the bottom term squared. So square square makes it a 4. Now, notice there's a lot of 1 minus x's, so I can, at the very least, I can cancel off a single 1 minus x off of each term. So there's a single 1 minus x there, there's a single 1 minus x there. That leaves us with 3 1 minus x's there. So what do we have now? Well, minus minus makes a plus. So we have 1 minus x plus 2x, which is really 1 plus x on the top, and downstairs 1 minus x cubed. But we're not done yet because we really want to get that to x to the n. So one more step. Again, same as before, times by x. So we get the sum 0 to infinity of n squared x to the n is equal to, times by x on this side, x plus x squared. Divide that by 1 minus x cubed. That's the first question. Express this sum as a rational function, a ratio of polynomials, and we have succeeded. Woohoo! Nice. Now, round 2 of the problem. So, round 2 says find the sum from n equals 0 to infinity of n squared over 2 to the n. Now, odds are pretty good we don't want to start from scratch. So we look at this and say, hey, does this expression, n squared over 2 to the n, look like n squared x to the n? Now, kind of the thing to clue off of is to say, hey, x to the n, that really looks like the part that's being used as the exponential part. So, there is an exponential part here. This is the same as the sum n equals 0 to infinity. I'll write it as n squared times 1 over 2 to the n, which is the sum n equals 0 to infinity of n squared times 1/2 to the n. Now, here's the big insight. It's the big aha. That piece right there, this is our x. That's what we have. That's x. And once you see that, you're like, oh, it's like n squared x to the n, but for x equals a very particular value, x equals 1/2. See, this is for x, and we didn't explicitly state this, so let's go ahead and actually state this over here. Where is it true that the sum of x to the n is 1 over 1 minus x? The answer is that this is true for absolute value of x less than 1. Now these operations of taking derivatives and multiplying by x hasn't changed it, except possibly at the endpoints, but it's easy to check. It doesn't work there. It's true for any x as long as absolute value of x is less than 1. Well, true story, a half in absolute value is less than 1. So that says come into here and plug in a half. So we get that this is 1/2 plus 1/2 squared divided by 1 minus 1/2 quantity cubed. Now, downstairs, what do we have? Well, it's 1 minus a half, that's a half, cubed, that's an eighth. So that can come up. So we have 8, that's from our downstairs moved up. Then we have a half plus a fourth. Well, 8 times a half is 4, 8 times a fourth is 2, and 4 plus 2 is 6. And therefore, the sum from 0 to infinity of n squared over 2 to the n is 6. Wow, that's cool. It's cool that we can find these things. And, you know, yes, it's a little bit of work, but when you think about how much work is actually involved, we didn't have to add up infinitely many things. Instead, we were able to adapt our tools from things that we already knew to get the answer for things we wanted to know. And that's a beautiful idea. Well, that brings us to the end of this quiz. I hope you had a lot of fun. I know I did. Take care of your health, and we'll see you next time. Bye.